As we continue working with the fundamental theorem of calculus, we also revisit the mean value theorem. The mean value theorem has applications to derivatives, which we learned, which is connected to then the antiderivative. You should be able to do it backwards. If you can do the mean value theorem forwards, you should be able to do it backwards as well. All right, so that's what we're going to tackle today in terms of our definite integrals. So just to set the stage for where we have been the last 2 weeks, we have now been introduced to the concept of area, the development of the perfect area. We pursued that from the geometric perspective and getting better and better and better and better. Then we saw how the antiderivative could help us when geometry didn't fail us, provided that the antiderivative is something we know how to do. And if that all fails, if we can't do geometry and we can't do an antiderivative because it's a function that's too hard or too complex, then Math 9 bails us out at the end as the other way to find the exact value. So that's where we've been. That's a roadmap looking backwards. This should be familiar to you as the mean value theorem. The mean value theorem says that assuming that the function is differentiable, which means it's already continuous, it has no corners or cusps, it's a closed interval, then at some point the secant slope, which connects the two endpoints A to B, should be parallel or equal to the tangent slope, which is the derivative. So this is from first semester. Okay, if you connect the endpoints, so just remember as a visual, if we have any differentiable function with two endpoints, if we connect the endpoints, that at least one time there should be one spot on here that also has the same f prime value. So that's the f prime of c parallel to the f of b minus f of a over b minus a. Okay, so that's old stuff. Now let's make the connection to new stuff. So suppose that you are told the function is twice differentiable. That is telling you that you can take the mean value theorem one step farther. And so the mean value theorem gets converted. In my mind, I think down a level. So I would say, then it also is true that the f double prime of c would be equal to, so everywhere there's a prime, I add another level of a prime. So because there was f prime of c, I'm adding a double prime. And then everywhere on the other side, where there's the function, I'm adding a prime. So it would be f prime of b minus f prime of a over b minus a. There's no primes to add there because there's no function value. That would also be a true statement at least once, which means the concavity at that point is equal to it doesn't have a super nice equal to the overall, it's to the average concavity. You don't need to necessarily think of it geometrically, but it is a true statement that would be true. What if it was thrice differentiable? Then what would that look like? Then do it again. Then the third derivative would be equal to the subtraction of the second derivative. So all of that is true, yeah.
It would still be b minus a.
Yeah, because that doesn't have any f on it. Yep, so there's no, that doesn't impact it at all. Okay. Then it should also be true that you should be able to go, if I think of that in my mind, I think of it as going down. I don't know why I think of the primes going down, but I do. But if you can go down, what else should you be able to do? You should be able to go up. All right, so what would it be like if I did anti of that? So what would, if I took my f prime in the green box, f prime and then f of b minus f of a would be minus a. If I went up a level, what would the f prime turn into? F. No, still f prime turns into just regular f. What turns into big F? On the other side, it would turn into big F. Okay, and that is also true. So the mean value theorem is powerful in all directions. Okay, in any direction that you want.
What's after
Some people do like adding another line like that, like bolding it. Other people will do just add the integral symbol to say, okay, the antiderivative of that, and do it again. So this is where you get to multivariate calculus, because there's double integrals, triple integrals. Okay, so this will be Calc 3. It's like next. You're just keeping doing, but remember, every time you do an integral, you got to remember a plus c. So then if you do a second derivative, you're going to have the plus c, and then you're going to have a plus d, and every time you're going to do it, you're going to add additional integrals. Okay, it just keeps. Well, then you start getting into integrating in 3 dimensions. Like you'll do relative to the x-axis, the y-axis, maybe the z-axis.
25 integrals. When you got to x, would you have to get rid of x?
Oh no, you add. There's Greek letters. There's all kinds of other letters you could use for sure. Subscripts, yes. All right, so this one has its own special name, and it is called the average value as opposed to the average rate. It is called the average value. All right, so that's the next slide. The average value is defined as f of c equals capital F of b minus capital F of a over b minus a. And where does capital F of b minus capital F of a come from? It comes from the integral, doing it that way. So that's what the integral looks like.
Do you do the integral twice, or do you just do it once?
Just once. All right, so there's a little memory trick that I like to associate with average value. Anytime you are asked to find the average value of something, it is the integral divided by the interval. Integral divided by the interval. The integral would be the integral going from a to b of the f of x dx. The interval is the subtraction of b minus a. Now this definitely has a geometric representation. This is going to also help you, like any word problem where it's like, find the average value of the number of bananas that were sold, or, okay, it's the integral of the number of bananas divided by the interval of the number of bananas. Remember, speaking of units as the word problems, okay, if f of x, let's say, was pounds, f prime of x, and we were doing this relative to, let's say we're doing it relative to minutes or time, what would the derivative units be? Pounds per minute. And then we do double derivative. That gets me to pounds per minute squared. So I'm dividing by the minutes. What if I do the antiderivative? What's the units on the antiderivative? Still pounds. Do the opposite of what you were doing before. Times minutes.
Pounds?
Pounds minutes. Okay? And then if you do it again, the antiderivative of that is going to be pounds times minutes, or pounds times minutes squared. Okay? Have you ever heard like a foot pound? You ever heard that a measure of a force?
Oh,
Okay.
Newton seconds.
Yeah, okay, so that's that measure of force is measuring, okay, measuring that. That's where, so force is the antiderivative. That gets into whole other stuff that we're going to do. But that's the way units are going to work. It's multiplication instead of
Like pound minute squared.
division.
Or pound minute minute.
Okay, like a newton.
Oh, but like pound minute. That just feels wrong.
It feels wrong. The other one only feels right just because you've done it for so long. You've normalized it.
Like pound minute feels fine. It's like meters per second. That makes perfect sense.
That's because you've been doing it a long time, so it feels good.
You got meters for a second.
All right, here's what the average value represents. Okay? imagine that you have a wave pool, okay? Or even just like a little aquarium, and you shake the aquarium or you stir it and the water is all wavy, okay? And then imagine that enough time has gone by to where the water is completely still. What is true about the volume in either situation? It's the same, right? So if you have it in waves or if you have it in smooth, the amount of volume hasn't changed because you're in a contained environment. Assuming that water's not splashing out of your aquarium, and okay, assuming that all the water remains contained. That is called the settling of the height at which, or the depth at which the water settles. That is called the average value. So if you take a curvy function, and if you were able to flatten that to an average height, that would be called the average value of the function. And you get it from doing integral over interval. That turns out to be true here. So here we've got, if we find the area, which is a little under and then a little over, the area is found by the integral from a to b of f of x dx, which turns out to be capital with f plugged in plus c, minus capital with a plugged in minus c. So if you don't mind, I'm just going to erase my plus c and my minus c right now. So I'll erase those, and I'm just going to write this. Okay. That is equal to the area of the rectangle. And the area of the rectangle is the base of the rectangle, which is what? B minus A is the base. And the height of the rectangle, which is what? F of C is the height, base times height. So we are saying that those are all equal, that the blue area of the rectangle and the yellow area of the curve, area of the curve are all the same. So let me summarize what we have. We have B minus A times F of C equal to F of B minus F of A, that those two things are exactly the same. Okay, that this,
But that was integral over the...
yeah. So this is equal to that. So I've tried to color code it. Yellow is the yellow area is the yellow.
I didn't see what
okay.
FC was. Never mind.
And then blue is blue. What does the fundamental theorem, the average value, the mean value theorem say? It should start with f of c. So how do you get f of c by itself? Divide. And so f of c by itself is capital F of b minus capital F of a over b minus a. So we've just proved what we said, okay? Which is integral. This part is found by the integral over interval. So whenever you read, you have to read discerningly. Not every time you see the word average, but specifically to average value. Don't get confused with average rate. Average rate is from first semester. Average value is now from second semester. So you want to be able to distinguish those two things in your head. And so I'll just summarize that for you. Average rate, first semester, f prime of c equals regular f of b minus regular f of a over b minus a. That is average rate, first semester. Average value deals with antiderivatives. So it will be f of c, not f prime of c, but regular f of c is the integral over b minus a. So they're both over b minus a, but this is a prime and that's not. And this is lowercase subtraction, whereas this turns out to be uppercase subtraction. So read discerningly to what they're asking you to do. It is not uncommon for an FRQ to ask you for both. In one of the parts, they might ask you for average rate. In the other part, they're asking you for average value. Average rate has to do with the slopes being parallel. Average value has to do with the, which means equal, right? Slopes being equal. Average value has to do with the areas being equal. The area of a curvy section compared to the area of a rectangle. That there is some rectangle that has the same area. Yeah, Jackson.
Oh, no, I was just gonna say, so that C that we found represents when the area is equal?
It represents the spot on the x-axis, which you could then figure out how tall it would be, but it figures out the spot on the x-axis that that's happening. Just like C here was the spot where the two were parallel. And C here is the spot on the x-axis where the areas will be equal. Okay? All right, so let's do a couple. Find the average value of the parabola from 0 to 4. Okay, the average value of the parabola from 0 to 4. Okay, so if I just do the math, the average value is the integral from 0 to 4 of the function 2 minus x squared dx over the interval of 4 minus 0. That's just the math on it. Then you do your antiderivative. Antiderivative is 2x minus a third of x cubed, or x cubed over 3, plus the constant c from 0 to 4, still over the interval of 4. So I do my antiderivative. Then I plug in and I evaluate. 8 minus 64 thirds plus c minus 0. All over 4. All right, which 8 minus 64 thirds is 24 thirds minus 64 thirds all over 4. Oops, negative 40 thirds over 4. Am I doing all my math right? Anybody finding anything I'm doing wrong? To the visual representation. So the visual representation is going to be our x-axis, a parabola. Parabola starting at 0. Parabola is going to cross the x-axis and then come all the way down here to be way down low at the number 4. So it should make sense to us area-wise. Okay, there's my, and I've got area. And then there's all this negative area down here as well. Okay. So what does negative 10 thirds represent? Negative 10 thirds represents where, well, it's the f of c value. Okay, it's not the c value, it is the f of c value. So negative 10 thirds represents f of c. That's a y value. So that represents where the y value should be for you to draw a rectangle that would have the exact same amount of area as the green and the yellow combined. So we want to go to negative 10 thirds on the y-axis, which is about right here. Draw a rectangle. And that rectangular area from 0 to 4 is going to be exactly equal to the combination of the yellow and green. the positive yellow area, the negative green area combined will equal the red area. The final question is, what's the x value for that? In other words, what's the intersection right here of where those two things happen? So what would you set equal to each other to solve that? Yeah, so you would set that negative 10/3 equal to the function, which is 2 minus x squared, and then you would do the algebra to solve that. That's just a basic algebra problem. Subtract 2 from both sides. So that's going to give you negative 16/3 equals negative x squared. Divide both by negative 1. So then x is going to be the square root of 16/3. Plus or minus technically, but we want the positive one because we're dealing with the quadrant or the interval between 0 and 4. So that's the x value where it happens. So you have the math, and then you have to, like, does that make sense? Should I have a negative rectangle? It should make sense to, it makes sense to me that I should have a negative rectangle because there's more negative area. There's more negative area, so the average value has to be negative. Yeah?
Do you want us to do that check if it's on a visual test or something?
Often it'll say, what's the visual, does it match the visual representation? Yeah. Okay, let's try again. Find the average value on 3 plus x minus 2 from 0 to 3. And this would be a non-calculator problem. Of course, I didn't use my calculator last time either, but this would be a non-calculator problem as well. So the average value, mathematically, is going to be the integral from 0 to 3 of the function 3 plus absolute value x minus 2 dx all over the interval, so the integral over the interval. Last time, I used the antiderivative to find the integral. I can't use an antiderivative this time because there's no antiderivative for an absolute value. So what strategy do I use instead if I can't use calculator?
Geometry.
Yes. Okay, you're going to use geometry to find it. You can't use it, so you got to be well versed in all three. You can't just say, I'm going to put all my chips into antiderivative, because there'll be times where you can't do antiderivative, or all my chips into calculator. We're going to need to do the geometry on this. So this is going to be shaped like what? It's going to end up to be a couple, maybe triangles, but what does the absolute value look like? A V. Where's this V been moved? Up 3 and right 2. So here's 0, right 2, up 3. So I have an absolute value graph, and my interval is 0 to 3. So my shape is not to scale. So what does my shape look like? You can do it a couple different ways. Yeah, I mean, I heard Jonathan say he wants to do 2 triangles and a rectangle. That's one way. I heard somebody else say 2 trapezoids side by side, a bigger one and a smaller one. Okay, either of those are going to be fine. This trapezoid is 3 high. Oh, no, wait. 4 high. This trapezoid is 5 high. And then this one is 3. So, you know, however you want to do it. If you want to do 2 triangles and a rectangle, or if you want to do 2 trapezoids, it's fine. So then we're going to do area to find these values. So my big trapezoid will be 1/2 with a base of 2 and heights of 5 plus 3. That's one trapezoid. So we'll call that the green one. And then next to it, we have another trapezoid. 1/2 of 1 is the base, times 3 plus 4. We'll call that the yellow trapezoid. and it's all over the interval of 3. So then you're going to do the math to figure that out. So that'll be 8 plus 7 halves over 3. In other words, 16 halves plus 7 halves over 3. So 23 halves over 3, or 23 sixths. So what does 23 sixths represent? Is it a position on the x-axis or the y-axis? This is the y-axis. This is the f of c value. So 23 sixths is a little bit shorter than 4, so about right there. And that represents the position of the rectangle whose area would perfectly equal the, a little bit higher than that. Probably more like that. Do a little bit higher, closer to 4 than 3. That area of the red rectangle is going to perfectly equal the green and the yellow combined. And then the question is, where does it occur on the x-axis? So you have to work backwards. You would need to take 23 sixths and set it equal algebraically to the equation. 23 sixths equal to 3 plus absolute value x minus 2. So then you got to go back to your Algebra 2 skills. Even, Mr. Lever, do they do solving absolute value equations in Algebra 1 even? Yeah? All right. Got to go back to remember how to solve that. 1A even does it. Okay? All right. So if we subtract 3 from both sides, we're going to get 5 sixths when we subtract 3, which is the absolute value of x minus 2. Do you remember how to take absolute value bars off when you're solving?
Yeah, you gotta do.
It's plus or minus, just like with a square root. So when you take those absolute values off, it's either the plus or the minus of 5 sixths. So that'll be plus or minus 5 sixths equals x minus 2. So x has to be 2 options, 2 possibilities. So either x is 17 sixths, or x is also 7 sixths. Yep. So it's happening twice. And that should make sense to you, because look at this line at the top of it hits it in 2 places. It hits it right here, and it hits it right here. So both of those are positions where the average value is happening. Yeah?
What does, I know it's f of c, but what does that mean?
F of c is the height along here. It's the average height. If you took, okay, so imagine you had infinite rectangles. How skinny would all those rectangles be? Super thin, right? So if you took all the rectangles ever possible, you took a whole list of all their heights, and you averaged all their heights together, you're going to get 23 sixths. It's the average of the value of all the heights possible. And that's kind of where you settle. Yep.
Now, why, if the height is 4?
It's not.
Oh, it's
I
not.
was
Okay.
I was saying it's close. 23 sixths is just a little bit under 4. It's barely under 4. 24 sixths would have been 4 exactly.
Yeah.
So my thing is not perfectly to scale. I should even be a little taller than what
So
I
4 is
actually
not the
was.
height, that's not what
No,
you're saying.
no. I was just trying to label where 4 was. I should label it as 23 over 6. All right, last one. Find the average value of a natural log on 1 to 5. So the math will be the integral from 1 to 5 of parentheses 5 plus ln x over the interval of 1 to 5, 5 minus 1. So this time, I can't do geometry because a natural log is a curvy thing, and there's no good geometry that fits perfectly under a curve. I cannot do antiderivative either. What's the antiderivative of 5? What's the antiderivative of natural log? There is no antiderivative for natural log.
Oh, I thought it was a close.
Okay. Oh, there's a derivative for natural log, but there is no antiderivative for natural log. So your only choice is math 9 at this point. All right, so at this point you would do math 9, to find the value of that and then divide it by 4. So then you're going to grab your calculator and you'll go from 1 to 5. You'll do the antiderivative of 5 plus the natural log of x.
Is there really no one for the natural log, or is there someone already there?
Not yet. So 24.047 over 5 minus 1, which is 4. So I get 6.012. So then if I were to make a visual representation of this, a natural log shifted up 5 is way high like that. Okay, going from 1 to 5 is going to make a non-geometric area, so it's just an area like this. And then 6.012 represents the height of where a perfect rectangle would be, which would have an equivalent area to the green that was under the natural log. So that would have a height of 6.012. That does not tell me where the x value is. The x value is what I would have to take 6.012, set it equal to 5 plus ln x, and then solve that. Or use the intersect feature on my calculator. Using the intersect feature on the calculator would be fine also. But I could subtract 5, 1.012 equals ln x. So x must be e to the 1.012. And that is the position of x on the x-axis, so about right there, e to the 1.012, which is going to be in the ballpark of 3, close to 3, a little bit less than 3.